So, hello everybody. I hope that you can hear me. It's exactly 6 o'clock right now, so we are about to begin. Long time no see. We're not seeing yet each other, but anyway, we still have the chance to meet even in under these situations. So I would like to welcome you all on behalf of the board of the Hellenic chapter of ASHRAE in this in the first our first webinar that it's about the ASHRAE position document on airborne infectious disease. Presenter is Professor Ljubomir Jankovic, that you can see him obviously in your screen. I would like to have a warm welcome to him as well. So just before we begin with our webinar, I would like to have the chance to say a few words, because it is a long time since the last time we had the chance to meet. As you can understand, we are now facing a situation that it's quite unique and peculiar for everybody. So we have to adjust to this new situation, and so we have to change. We were forced almost violently to change a lot of things that we were doing and how we were operating in our normal way. So what we are trying now to do is to introduce something new, so as to keep in touch and also to keep informed as much as possible on this new thing that we have right now, which is the COVID-19, the new pandemic that it has forced us to operate in this way. So we are opening it from our behalf as well. ASHRAE has already opened the discussion so far, and we are opening it as a chapter as well right now, this situation, beginning with this webinar. First of all, I would like to thank all members of the board, of our board, for their continuous effort. We are still operating. We're still trying to find the ways to help you to support everybody for this situation. I would also like to thank all of our sponsors that they are here and they are supporting us as well. I would like to say also that ASHRAE, as I said, is active, is trying to do what is best for this situation. As you can see the presentation that it's on your screens right now, there is a special site that it's on the top of the screen, the www.ashrae.org technical resources at resources, where you can find all available resources that ASHRAE has made public for everybody, so as to see what is the situation here with the COVID and how are things advance, and they are advancing every day, and they are keep updating every day about how we can deal with this new situation, how we can deal with the virus, what are the optimum ways to react and help our situation and our buildings and our environment on that. And also, as an Hellenic chapter, and they have also employed a task force, a special task force, especially on that. You can find that on that particular site. And also to help the task force on that, the chapter has recently sent you an email regarding a questionnaire where we would like to have you all participate in any way you can, and provide the information that you probably have on that issue, so we can pass it on to the task force. You can find the questionnaire in our site, and it's still open, although we have sent some first feedback, but the information is continues. So please share your feedback, share your thoughts, share your experiences on that. And by all means, if you have something to offer or something to say, the chapter is available and we can use your help. Don't hesitate to contact us through our mail. It's also in the presentation, bod@ashrae.gr, to help you about that. Just a brief say, we had a lot of events as a chapter organized for the past 2 months, but none were successful. We had the 2 energy buildings, one in Cyprus and one in Thessaloniki. We have to postpone those. We have not forgotten them. We will try to do our best, and we will see how the situations will proceed. And probably we will arrange that in a later stage. Also, there is this quite big and interesting event that is planned for September. The IEQ, the joint conference with ASHRAE and IAVC. IAVC, for those who are not familiar with that, stands for Air Filtration and Ventilation Center. It is the information center established by the International Energy Agency for Energy Efficiency Ventilation. It is a very famous conference on the matters of energy efficiency ventilation, held every 3 years. And that year we had the honor and the opportunity to organize it here in Greece, and the Hellenic chapter to be the host of this conference. It is not yet postponed, it is not yet cancelled, it's still active, but they are also keep track of what is going on, and they will have a further announcement on that. You will find that on our site as well, where what is going to do and what is finally going to do about that. We will keep you updated on that as well. Also, we have energy buildings and energy transportation 2020. Usually we have this, apart from last year that we had the CRC as well. Usually we do that on early November. We are planning to proceed with that. Probably made it that earlier, maybe early October. We will see about that. We'll keep on track on that. We will inform you about that as well. Our aim and our target is to have that conference to make that conference, but also it will depend how the whole situation with the COVID-19 will proceed. And also we will inform you. This is the first webinar. We're planning and we are hoping that we will have some other webinars as well in May or June, and we'll keep you informed on that as well. Last but not least, and I will finish with that, and I will pass it on to Lubo. Also, I would like to remind you that ASHRAE, the Hellenic chapter of ASHRAE, is participating in the European program with the name of Light Coke. Light Coke stands for lightweight materials of concrete and ceramic materials. And the title of the program is Building an Ecosystem for the Upscaling of Lift-Weight Multifunctional Concrete and Ceramic Materials and Structures. The aim of this project is to make and to provide the ecosystem with a singular entry point to small and medium enterprises and to industry, so as to cover the gap in the upscaling and testing of multifunctional lightweight concrete and ceramic materials. The Hellenic chapter is part of that, is one of the partners of this program, and the program still goes on. And as soon there are 26 partners from across 9 countries that they're participating. As soon as we have some news or updates about that, we'll have them on site as well, and we'll let you inform about that as well. So I think I talked too much. Probably I had a lot of time to do that, so I overdone that. So with no further delay, I would like to present once more Professor Ljubomir Jankovic. Professor Ljubomir Jankovic is from the University of Hertfordshire and is also the president of the UK London chapter of ASHRAE. And I would like to thank him once again for joining us, not being here with us, but anyway, joining us and having this webinar on he will be presenting us the ASHRAE position document on airborne infectious disease. One last thing, if you have any questions, you can post them in the chat panel of your dashboard that you can see on your right-hand side, sorry. And there will be time at the end, so you can write down your questions, and then we'll have time at the end address these questions to Professor Jankovic, and we will have the chance to discuss about them. So I'll pass the presenting to Professor Jankovic, and that's all for me. Thank you very much once again.
Thank you, George. Okay, I hope you can see my screen now.
Yes, we can see it. Yes, we can see your screen. It's not yet in presenting mode, but we can see your screen. Okay, now it's great. Okay.
All right. Okay. Well, thank you, George, for the introduction, and for the audience, you can probably figure out that although I'm from the University of Hertfordshire, I'm originally from Serbia. You can tell that by my name. So when I said to my mother that I'm going to do this presentation to a group of engineers in Greece, she asked me, "Are you going to speak Greek?" Well, no. So I'm sorry, this has to be in English. And this is my personal view of the ASHRAE position document on infectious aerosols. The presentation is entitled Airborne Infectious Diseases, and this is part of ASHRAE COVID-19 Preparedness Resources, and the presentation is especially for the Hellenic chapter today. By the end of this talk, or at my last slide, will have an address from where you can download the handout. So you don't need to write, it will be available immediately after the talk, and you can just sit back and relax. I just need to give you a bit of history about this document. The position document entitled Airborne Infectious Diseases was initially approved by ASHRAE in June 2009. And that document went through multiple revisions until February 2020. And it was then superseded by the new position document entitled Infectious Aerosols on 14th of February. So at the time when we were organizing this talk, we were still working under the Airborne Infectious Diseases document, but since that time, ASHRAE has withdrawn the old document that is superseded by the new document, and that's the basis of this talk. So the presentation scope is to reference ASHRAE resources in the context of the COVID-19 outbreak, and to provide an overview of ASHRAE's approved position document on infectious aerosols relating to the operation of heating, ventilating, and air conditioning systems, and to discuss practical implications for building owners, operators, and engineers. The original resource on which this is based is on this website, which George also referred to, and that website includes the position document on infectious aerosols. A word from the president of ASHRAE, Daryl Boyce, who says that ASHRAE recently announced the creation of the ASHRAE Epidemic Task Force to help deploy ASHRAE's technical resources to address the challenges of the current pandemic and future epidemics as it relates to the effects of heating, ventilation, and air conditioning systems on disease transmission in healthcare facilities, the workplace, home, public, and recreational environments. Members will be kept informed as ASHRAE adapts to these rapidly changing circumstances. And pretty much every time I log into that website, there's something new there. So I suggest you keep visiting it and checking, because there's new information being posted almost on a daily basis. The Preparedness Resources page contains a variety of documents, including recommendations of the ASHRAE Epidemic Task Force, ASHRAE Position Document on Infectious Aerosols, Environmental Health Emerging Issues Brief, guidance documents, press releases, ASHRAE Epidemic Task Force featured in media, and others. But this talk will focus on the position document on infectious aerosols. This document provides the information on the following: the modes of transmission of airborne infectious diseases, the implications for the design, installation, and operation of heating, ventilating, and air conditioning systems, and the means to support facility management and planning for everyday operation and for emergencies. The position document covers the spread of infectious disease by small airborne particles or aerosol that contain microorganisms, but the position document does not cover transmission via direct contact with individuals or surfaces. Effective transmission prevention strategies include dilution and extraction ventilation, pressurization, airflow distribution and optimization, mechanical filtration, ultraviolet germicidal irradiation or UVGI, and humidity control. Airborne dissemination or generation of airborne particles occurs through coughing, sneezing, shouting, breathing, toilet flushing, some medical procedures, singing, and talking. And this is the diagram of aerosol movement. When an infected person exhales droplets, they become mixed in the air through turbulence, and larger droplets travel with a ballistic trajectory to longer distances. As droplets evaporate, they become droplets nuclei. While they are still in the air, droplets are swept by the air and they fall due to gravity, but their fall is resisted by a drag force. When the droplets land on the surface, they dry and become desiccated, and bed-making activities and even walking can eject dry particles back into the air. Many documents state that a safe distance is up to 2 meters from the infected individual. However, there's new evidence that particles can travel further than 6 to 8 meters. And as you will see on the next slide, particles of 0.5 microns can be suspended in the air for over 40 hours, and particles of 1 micron, 12 hours, particles of 3 microns, 1.5 hours, particles of 10 microns, 8.2 minutes, and particles of 100 microns, 5.8 seconds. So if particles are going to be suspended that long in the air, like 41 hours for smaller particles, then the 2 meters distance is not a safety distance anymore, and some other measures need to be put in place. Based on my research, so this is not ASHRAE from ASHRAE document, but based on literature review, I found that breathing exhales particles at a velocity of up to 1 meter per second, and they travel to a distance of 1 meter. Coughing exhales particles at a velocity of 10 meters per second, and they travel longer than 2 meters. And sneezing exhales particles at 50 to 100 meters per second, and they travel up to 8 meters distance. But as I said, small particles in still air can be suspended for a long time and can travel just about anywhere within the room. So that is something that really needs to be taken into account. Exposure to airborne infection, D, is directly proportional to number of infectors, a number of people who are infected, a number of doses of airborne infection, also directly proportional to pulmonary ventilation per person, ventilation of lungs per person, and the exposure time, and indirectly proportional to the volume of fresh or disinfected air. So there is a Wells-Riley standard model of airborne infection, which looks like this, where C is number of new infections and S is number of susceptibles, a number of people who are susceptible to infection. And we've seen the degree of exposure to infection on the previous slide. This is the expression in the exponent here. And the expression in the brackets is probability of a single infection. So if we now have a look, what influences the increase or reduction of probability of a single infection? Reducing I, or people density, decreases exposure. Reducing Q, or number of doses, presumably taking more than 2 meters distance, decreases the exposure. We cannot do anything about pulmonary ventilation per person. This is individual. Individual variable. Each one of us breathes at different rates, different volumes. But the exposure time is very critical. So reducing exposure time, duration in high density areas decreases exposure. And I should say at this point that there's evidence that one of the first infections that occurred in Wuhan in China when it all started, occurred during a conversation between 2 people over the market stall during a 15 seconds conversation. So you're talking about seconds of exposure rather than any longer period of time. And finally, increasing amount of fresh or disinfected air decreases exposure to infection. Just to see how these numbers work, so if we set the degree of exposure to infection to 0.1, so this is the exponent in this equation, then the probability of a single infection is, sorry, we went back, probability of a single infection is also 0.1. But if we set the degree of exposure to infection to 0.99, then probability of a single infection rises to 0.63 or 63%. So it gets much higher. So transmission through HVAC systems and interzone airflows must be considered as means of airborne infection transmission. And in that sense, HVAC systems may contribute to both transmission of disease and potentially can reduce the transmission risk. In healthcare facilities, and this is now looking at practical implications for building owners, operators, and engineers. In healthcare facilities, indoor air management has become critical to successful prevention. And multiple modalities need to be used simultaneously. This is found to work well. For example, when you combine administrative regulations, environmental controls, and personal protective equipment protocols. In terms of ventilation and air cleaning strategies, laminar and other in-room flow regimes need to be considered. Differential room pressurization needs to be considered. Personalized ventilation, source capture ventilation, filtration, either central or unitary, relative humidity, and upper room ultraviolet germicidal irradiation, or UVGI. And we will look into all of these individually. In terms of ventilation and air cleaning strategies, ventilation therefore represents a primary infectious disease control strategy through dilution of room air, as you've seen from Wells-Riley equation. Highly efficient particle filtration is also likely to reduce the airborne infectious particles, and directed supply and or exhaust ventilation is important in several settings, including operating rooms. And of course, exhaust capture ventilation is also important. And just to say something about that, imagine having exhaust ventilation from an infectious ward, from a room where there's infection. You cannot exhaust that type of air directly to the outside, because if there are people walking around the hospital, they can get infected immediately. So that air needs to be filtered before it is exhausted to the outside. So just to revisit the dilution of air, in a situation where we have a risk of infection, we want to go for 100% of fresh air intake, and we don't want to go for recirculation. So 100% of fresh air intake is very important to dilute air and reduce risk of infection. Now, in terms of filtering, let's just see what kind of particles we are dealing with. Cough-generated particles, droplets, can be of the size of 0.65 microns to 3.3 microns, but exhaled breath droplets can be 80% in the range of 0.3 microns to 1 micron. Now, coronavirus size is around 0.12 microns, 0.12 to 0.16 microns, and therefore can be easily contained in droplets exhaled by individuals. We also know that HEPA filters eliminate 99.95 to 99.97% of droplets of size of 0.3 microns and above. So HEPA filters need to be used to reduce the risk of infection. And ultraviolet radiation can be combined with filtering. When it comes to airflow strategies, there's evidence that unidirectional low velocity flow works in a similar way as a piston in the internal combustion engine, as it cleans everything in the space in which it operates. And that is pretty much achieved by single space high efficiency filtration units that achieve directional airflow. When it comes to high velocity turbulent flow, that type of flow isn't equivalent to a piston that cleans everything from the space in which it operates. And it is very likely to spread particles, droplets all over the room. You cannot capture them very easily because they are spread out, and that can contribute to increase of transmission of airborne infection. Ultraviolet radiation is a very interesting principle to reduce infection of airborne transmitted by airborne particles. UV radiation needs to be in the UVC spectrum with wavelength of between 100 to 280 nanometers, and that kind of radiation deactivates or destroys RNA or DNA, and the optimum wavelength is found to be 265 nanometers. Now, if you think that when the weather gets nicer around the world, especially in Greece, and sun starts shining, that you will have quite a lot of UVC radiation. Well, you won't, unfortunately, because UVC radiation hardly ever gets to the surface of the Earth, simply because it is absorbed by the atmosphere and by the ozone layer. However, there are lamps that can be purchased on the market that provide this wavelength of radiation, and you can very easily install this kind of disinfection system in HVAC systems. UV radiation can penetrate the other surfaces of the eyes and skin, and therefore the eyes are very susceptible to damage, and shielding is needed to prevent direct eye exposure. Energy conserving strategies, including demand control ventilation, should be used with caution, and in my opinion should be completely avoided, because if we try to save energy and lose several lives as a result of that, that really doesn't make sense. So a natural ventilation used by operable windows is not covered as a method of infection control by most ventilation standards and guidelines, but in many countries, the transmission control measures include natural ventilation and social isolation. Now, room pressure differentials are important for controlling airflow between areas in a building. Airborne infection isolation rooms are generally kept at negative pressure with respect to the surrounding areas, and hospital rooms with immune-compromised individuals are kept at positive pressure in protective environments. This is how it works. So if you have airborne infection isolation room on the left, you would put that onto a negative pressure simply by running the fan that supplies that room slightly slower if it's a supply fan, or if it's extract fan, by running it slightly faster. And the opposite occurs in the surrounding rooms, where you need to achieve positive pressure. And pressure difference of several pascals, like 3-4 pascals, will do the job very nicely. In rooms with immune-compromised individuals, you need to achieve positive pressure, and in the surrounding areas, you need to achieve negative pressure, so that nothing goes into these rooms with immune-compromised individuals. In terms of personalized ventilation systems, they can be set to supply 100% of highly filtered or UV disinfected air, and they may be protective, but there are no known epidemiological studies that can justify the efficacy of these systems. So further research needs to be carried out. Temperature and humidity are important parameters, and whereas ASHRAE makes no definite recommendation on indoor air temperature and humidity for controlling infectious aerosol transmission, it is known that relative humidity between 40% and 60% is most unfavorable for survival of microorganisms. And this is also very favorable relative humidity for humans. So we need to keep relative humidity within these boundaries. And that can be achieved by proper selection, operation, and maintenance of humidification equipment in HVAC systems. Now, in relative humidity below 40%, there are 3 risk factors that increase infections. First one is infectious aerosols shrink to become droplet nuclei, and they are suspended in the air and travel greater distances. Secondly, many viruses and bacteria have increased viability in low relative humidity. And also, relative humidity below 40% impairs mucous membranes, barriers, and other steps in immune system protection. So not only that we lose our immunity at lower relative humidities, but we make the viruses and bacteria more viable, and aerosols shrink to become nuclei and are suspended in the air and travel greater distances. Now, in emergency planning, what is often done is control banding, risk management to apply a hierarchy of controls to emerging pathogens. And this needs to be based on the likelihood of the pathogen, duration of exposure to the pathogen, the infectivity, transmission capability of the pathogen. For example, at the time when infection started spreading in the UK, transmission capability was from one person to 3 other persons. But now this has gone down from 1 person to less than 1 person. So that needs to be taken into account. And also the virulence or severity of the pathogen is very important. And now let's just say we are talking about current COVID-19 infection, but we are also talking about future emergencies for which we need to plan now. Now, emergency planning also needs to work on increasing dilution ventilation, increasing relative humidity, or quickly applying upper room UVGI disinfection, ultraviolet germicidal irradiation. And this needs to be done provided that it doesn't create either flow of air to less contaminated areas or conditions of extreme discomfort. Creating pressure differentials may be the appropriate strategy, as we have seen from a few slides ago. And these actions should always be undertaken in collaboration with infection control professionals. But knowledge of the system operation and the nature of the source of the threat are very important. So ASHRAE positions, there's a number of points of ASHRAE positions now. All facility designs should follow the latest published standards and guidelines. And mitigation of infectious aerosols, dissemination should be a consideration in the design of these facilities. So effectively, these facilities need to have something built in, even if it's not necessary for the current situation, but for future situations, it may be necessary. So it is very advisable to have a bit of redundancy in the system that can cope with future epidemics. The design and construction team should, through integrated design, incorporate appropriate infection control bundle in early design stages, and buildings and transportation vehicles should consider designs that promote clean airflow patterns. Design of airborne infection isolation rooms should include anti-rooms, surrounding rooms where significant transmission risk through aerosols exists. The following should be included based on risk assessment: enhanced filtration with higher minimum efficiency reporting value filters over code minimum, upper room UVGI irradiation with possible in-room fans as a supplement to supply airflow, local exhaust ventilation for source control, personalized ventilation systems for certain high-risk tasks, portable freestanding high-efficiency particulate air HEPA filters, and temperature and humidity control. Healthcare facilities should consider design and operation to do the following: to capture expiratory aerosols with head wall exhaust, tent or snorkel with exhaust, floor to ceiling partitions with door supply and patient exhaust, and local air HEPA grade filtration. And this particularly refers to temporary facilities. I think we need to somehow pause and think about that. A number of temporary facilities have been created across Europe to deal with the pandemic. And there are large open areas rooms where patients are going to be situated. However, this is going to increase the spread of disease simply because if you just look at these recommendations, floor-to-ceiling partitions with door supply and patient exhaust need to be installed there, and these temporary facilities don't have that. Exhaust in toilets and bedpans is a must, and we need to maintain temperature and humidity control as applicable to the infectious aerosols of concern. We need to deliver clean air to caregivers, to staff who are working at the front line, and maintain negatively pressurized intensive care units where infectious aerosols may be present. More on the healthcare buildings. We need to maintain rooms with infectious aerosols where there's concern about these aerosols and negative pressure, but where we are absolutely sure then we need to provide that negative pressure. And we need to provide 100% exhaust from the patient rooms. We need to use UVGI, ultraviolet germicidal irradiation, and we need to increase the outdoor air change rate in patient rooms from 2 to 6 air changes per hour. We also need to establish HVAC contributions to a patient room turnover plan before reoccupancy. So suppose that we had a patient in a room infected with COVID-19. The patient has then left the room. That room needs to be treated by HVAC contribution before reoccupation by a new patient. In non-healthcare buildings, there should be a plan for an emergency response, and the following modifications to a building HVAC system operation should be considered. Increase of outdoor air ventilation, disable demand control ventilation and open outdoor air dampers to 100% of fresh air as the indoor and outdoor conditions permit. And also improve central air and other HVAC filtration to MERV 13 or the highest level achievable, and keep systems running longer hours, 24/7 if possible. Still about modifications of buildings other than healthcare buildings. We need to think about adding portable room air cleaners with HEPA or high MERV filters with due consideration to the clean air delivery rate. We need to add ducts or air handling unit mounted upper room and or portable UVGI devices in connection to in-room fans with high density spaces such as waiting rooms, prisons, shelters, and so on. We need to maintain temperature and humidity as applicable to the infectious aerosol of concern. And we need to bypass energy recovery ventilation system that leaks potentially contaminated exhaust air back into the outdoor air supply. And in general, we need to design and build inherent capabilities to respond to emerging threats and plan and practice for them. What this really means is that we need to have a redundant capability in many HVAC systems, and even that is going to cost more money. It is going to be money well worth spent when it comes to a situation like this, as you will probably agree and understand. So ASHRAE is committed to address research gaps with future research projects, and to partner with infection prevention, infectious disease and occupational health experts and building owners to evaluate emerging control strategies and provide evidence-based recommendations. ASHRAE are committed to educate stakeholders and disseminate best practices and create a database to track and share knowledge on effective protective engineering design strategies and update standards and guidelines to reflect protective evidence-based strategies. So this presentation was an overview with some of my personal professional interpretations, but for the original source, please consult the details on the COVID-19 preparedness resources website at this address. This will be in the handout, so you don't need to worry if you miss this slide. And that web page includes the document which was overviewed here. This is ASHRAE position document on infectious aerosols. I've also done some background research, and I don't expect that you can read and see all this, but it will be in the handout. So there's a number of references here where you can find about airborne particle generation, travel of airborne particles, and also velocities and dimensions and so on, size of airborne particles. So I hope that you'll find this useful. So thank you for listening. My name is Professor Ljubomir Jankovic from the University of Hertfordshire, and my email address is there and my contact details, and you can find these slides now on this address. So this is ashrae-london.com/latest.html. And this is the end of my presentation, and I'm now happy to take any questions or comments. Thank you.
Thank you very much, Professor Ljubo. So I think for the next webinar, I have to have a sound of clapping hands as well, because this is a sound that is missing right now. But I'm sure that we will have some if we are face to face. So thank you very much for your presentation. So I will go on to some questions that we have here. We have a couple of questions regarding ultraviolet germicide lamps, and
yes,
especially we have some, if they can work even in recirculation mode, and if they are safe to install the UVGI upper room UVGI in an office area or even in a house.
Well, okay. As far as recirculation is concerned, I think we need to be very careful. I think recirculation is really something that we need to try to avoid, because recirculation saves energy, but it's much more important to save lives now than to save energy. So I would advise colleagues not to really consider recirculation as something that should be used now. In terms of UVGI, obviously there is a risk to skin and eyes, and this can be installed in offices and in homes, but you need to be very careful that you will be exposed to that risk. So, for example, if you install it in an office or in a home, then it will be really advisable to wear sunglasses and to wear sun cream. So I guess that becomes less practical. But if UVGI can be, or if it's installed in air ducts, then that is much more kind of manageable proposition. Now, I've done some some simulations. I'm actually developing a simulation model of airborne particles, and I've just submitted an article to a journal. And I found that as these airborne particles evaporate, their volume becomes smaller, they lose mass, and they become more and more suspended in the air, so they start going up. And it is really very difficult to control them because they can go anywhere. So I think it is very important to have unidirectional flow ventilation that takes particles out, just like a piston in a internal combustion engine, and combine that with good filtering and good disinfection with ultraviolet light. So, sorry, this is a long answer to a short question.
Yes, and I also would like to add as well that, as we said before, the ASHRAE has the special task force about COVID-19. Professor Bill Buffett is the head of this task force, and there is also a presentation made by him, especially on ultraviolet lamps and this. So I think it is available also in this website. So anybody who wants some more information about that, you can seek cases on that. There are a lot of questions regarding recirculations or special issues. I will try to summarize it a little bit. We have there are some questions about case studies, like ones that we have cases with fan coils in the ceilings, in false ceilings, and then we have the fresh air coming into the false ceiling free, not directly with a separate grill. So what do you think that we should do about that, and should we keep the fan coil run constantly in order to have the fresh air recirculates in the room constantly, or should we do something else?
This is very difficult because there is evidence. I saw just recently an example from a publication, and I don't have the publication off the top of my head here now, but infection that occurred in a Chinese restaurant as a result of recirculation, where one person managed to infect 9 other people just because air was recirculating in that part of the restaurant. So I think it will be probably better to switch all recirculation off, because that just mixes up the particles. They're more in the air, and the infection probability becomes much higher.
Okay, and there are a couple of questions about the cases like that also, that what should do about filtering about that, and why should we maintain, what do we do about the maintenance on this kind of equipment? Should we change filters more often, and is there something else that we can do, and what we can do about maintenance for split units?
Yes, okay, filters obviously should be changed according to the technical documentation. If the filters are enhanced with ultraviolet radiation, then they probably don't need to changed very frequently, or more frequently than required by their technical specification. But HEPA filters will get quite many particles there, and I think the lowest cost in all this will be the cost of changing filters. So I would encourage changing filters perhaps more often than they would normally do. And at the same time, people who change filters should really wear full protective equipment, because there could be lots of viruses in the filters. What was the other was there another question combined with this
Yeah,
one?
no, it was if we, but I think it is covered whether we should do something in particular about, you know, small split type units, split time air conditions.
Okay, so these are unitary
Exactly.
units. Well, if these units serve single space, it depends. You know, if this is in a private home, then what you're going to get in that filter is perhaps well known. You know, if there is no infection there, then the filter can be changed as you would regularly change it or wash it. But if the filter is somewhere in an infectious environment, then these split units, I think the split units will probably recirculate quite a lot. So I would be inclined not to run them, but to have something temporary that just extracts the air from that room.
Okay. We have some more questions regarding relative humidity and especially that what is exactly they need more clarifications about the range that you have mentioned between 40 and 60%, and what happens, especially how if this is what it should be aimed, and also what is happening if humidity is above 60%.
Okay. All right. So within that range of 40 to 60%, that range was found to be less favorable to viruses and bacteria. So microorganisms don't like that range. They like more the range below 40% relative humidity. And in that range below 40, not only that they are more viable, but they also evaporate and become nuclei. These nuclei can be launched into the air very easily, and also people get decreased immunity because of the drying of the nasal and other systems. So above 60%, there is another extreme that these droplets will probably be suspended for longer period in the air. They will not lose as much mass as they would normally under lower humidity. So they would be longer in the air as droplets, and therefore they will present higher risk to infection. So high humidity will maintain the droplets longer. Low humidity will convert the droplets into nuclei, into viruses themselves, which can get suspended in the air. So neither extreme of those two humidity ranges works well. But what seems to work well is between 40 and 60%.
Okay, and one more thing, we have some questions as well regarding heat exchangers. There is quite a talk here also as well in hearing this, but I suppose it's everywhere. We have a lot of systems that they are ventilation system with only 100% fresh air, but we have them in a hose with heat exchangers, either plate heat exchangers or rotary heat exchangers. What happens with that, and what is what should we do about those? Should we turn them off? Should we bypass them, or what?
Well, plate heat exchangers where there's cross flow of air, but those streams of air don't mix. I think that is probably fine. But rotary heat exchangers are, I would say, an accident waiting to happen, because as they rotate, they will carry particles from exhaust side to pressure supply side. And it is now known that viruses can survive on metal surfaces, and these are primarily metal-based rotary heat exchangers. Viruses can survive up to 5 days, 4 to 5 days on the metal surface, and these rotary exchangers will turn within several seconds between exhaust and supply. So I would think that it would be really wise to switch those off. But the late heat exchangers with cross flow, that should be all right.
Okay. And let me try and come with the final question. We have a lot of questions, to be honest, but I don't think we have that much time. But anyway, some more things about filters. There are some concerns whether the available filters and also what we know about the size of the coronavirus, whether the available filters, even HEPA filters, are efficient enough, are efficient for this type of situation, and whether also another question is whether we can have a colonialization of virus in the filters.
Okay, the first question is about HEPA filters, and what happens with HEPA filters is that they eliminate particles from 0.3 microns onwards, and they eliminate 99.97% of those particles, and these are droplets that occur through breathing. So these are the smallest droplets that come out as a result of breathing. Now, virus size is 0.12 to 0.16 microns, and it occupies these droplets. Now, if droplets are eliminated, droplets are going to be eliminated by HEPA filters. But if the droplets dry and you know, these viruses become viruses on their own without inhabiting a droplet, then HEPA filters are not going to do the job. And this is where we need to have ultraviolet radiation to kill the virus. So I would say HEPA filters work as long as we have virus in the droplets and as long as we have humidity that is controlled within these boundaries. But to be sure, to be on a safe side, we need to think that some of these droplets are going to dry, become nuclei, and will contain viruses which are going to be passing very happily through the HEPA filters. Now, HEPA filters could well be colonies of viruses. So, you know, whoever changes or deals with HEPA filters needs to be very careful, needs to have full protective equipment to change them.
Okay, great. I think I have to pause, I would say here. We have to pause at some stage. I think the concern and the interest of everybody is very huge. Thank you very much for your thorough presentation. Okay, yes, one more thing I have to say for sure is, apart from questions, I have a lot of congratulations on your presentation as well, and it was a very interesting presentation, and I have this feedback right now from here. Also, on my behalf as well, I have to say hello to a lot of people that they are saying hello. I wish I could hear you, and we can say hello from close distance, not very close, but okay, quite close distance. And so, Professor, I would like to thank you once again. Thank you very much for your presentation. Thank you very much all for attending this webinar. We will have more, stay in touch, and also we will you will have emails apart from the site that Professor Jankovic told you, where you can find the slides. You can have also an email where you can find the presentation and the recordings of this webinar as well. So thank you all for that. Stay safe, stay well, and we'll be in touch and be back as soon as possible. Thank you very much.
Very much. Thanks for the invitation. It was a pleasure to be able to try to beat this thing together. Yeah.
Okay, yes, that's good. Thank you very much.
Thanks.
Bye-bye, everybody.